a binomial distribution is a specific kind of probability distribution. So we know probability distribution is when you can list all the different outcomes and the probability of each. In a binomial distribution, we have a set number of trials. So I could say I'm going to roll a dice 4 times, but I can't say I'm going to roll the dice until I get a 4. Do you see the difference? Because if I don't have a set number of trials and I'm just rolling until I get something, I don't know how many different trials I'm going to have at the beginning. So binomial, we have a set number of trials before it ever starts. They are independent. So we've had some examples like we are looking at, I'm trying to think of some of the ones we've done. You know, if I was just going to draw a card out of the deck, okay, then a standard deck has 52 cards. If I wanted the probability of getting a red card, what would that be? $52. So 26 out of 52 would be red. If I took out a red and then Carson drew one, what's the probability he got a red? 25 out of 51. So those are not independent because the probability of him getting a red changed after I took that one card out. But if I drew a card, got a red, and then put it back in, what's his probability of getting a red? The same. And so in that case, they would be independent. So independent means the same probability every time. For each trial, there are 2 outcomes, success or failure. So drawing a card, I can either get a red or I could not get a red. But I couldn't say, I'm going to draw the card and I want to know the probability of an ace or a king or a queen or a jack. There's too many different options there. So binomial, there are only 2 options, success or failure. And the probability of success is fixed for each trial. The probability of getting what you want is the same every single time. If that's true, then it is binomial. So let's take a look at some scenarios and decide if these would be binomial. So A player rolls a pair of die 10 times. The number X of 7s rolled is reported. So would that be binomial? Do we have a set number of trials? Yes, my number of trials is 10. Do we usually use P for the probability of success, Q for the probability of failure. So what would be the probability of success in this case? 7. Yeah, getting a 7. Okay, so P is the number of 7s. Well, I guess not really the number, the probability of a 7. And then Q would be the probability of not a 7. Is there any other option? No, there's only those 2 outcomes, so this is binomial. All right, B. An official with the FAA randomly selects airline flights until she finds 10 that were not on time. The number of flights that needed to be selected is reported. Is this binomial? No. No. Why?
Doesn't have a set number of trials.
Mm-hmm. Okay. C. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number of females is recorded. So, do we have a set number of trials?
Yes.
Yes. Do we have 2 outcomes, female or not a female? Yes. Are those independent?
No.
So if I'm going to select 4 students, once I take the first student, does the probability of the next one being female change?
Yes.
Yes. So this is not binomial. And the reason the trials are not independent. All right. Let's look at a problem. The 11 largest air carriers have an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected for May 2008 and the number of on-time flights is recorded. Construct a probability distribution for the random variable x using a tree diagram. All right, so how many trials do we have? 4. We're looking at 4 flights. P, the probability of success. In this case, a success would be what? On time. So the probability of being on time would be 0.79. So Q is the opposite. You're not on time. So how would we find Q? 1 minus 0.79. I am asking for a probability distribution. So that's when we make the table, the x, p of x. Okay, so my number of trials, if I'm looking at how many flights are on time, what are my possible answers?
0,
0,
1, 2, 3, 4.
1, 2, 3, 4. So those are my x's. All right, but I don't really know how to calculate the probability of these things. I could figure it out several different ways. Later in this section, we are going to have a shorter method for figuring it out, but I want to show you in a way we can see why this works, okay? So we're going to make a tree diagram. That's basically kind of listing out all the possibilities. So we are starting with the first flight, and either it's on time or it's not, right? So that is success or failure. So there's flight 1. And we have 4 of these, right? So when we get to flight 2, it can be either success or failure. So it could be that the first was a success and the second was a success, or the first was success and the second was failure, or the first was failure and the second was success, or the first is failure and the second is failure. So this is like my first flight. Now to my second flight. So what's going to happen when I do the third flight? What do I have to do? Yeah, we're going to branch off from each of these. If you've gotten to this point on the path, there's still 2 options. Okay, for every one of these, the third flight could be on time or it could not. So we're really just using this diagram to list every possible combination. You guys see how I'm getting this? We have 4 flights, so we need 1 more. So the fourth and final one. Almost out of space. So if we look at this fourth one, we see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16 different ways this could happen. So what we need to do is figure out what's my x in each case. Okay, we're kind of counting these things. So I'm going to add this here. For each of these 16, x, we're counting how many were on time. So the first option, success, 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 success. So that one had 4 on-time flights. When I did S, 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 F, that one had 3 on-time flights. Okay, so counting basically these, that gave me 4. This one had 3 on time. So then we go to paths. This path, which had 3 on time, or I could take this path that had 2 on time. I could go this way, which had 3 on time. If I go this way, it had 2 on time. If I do this, it had. If I had this, it had. You guys see how I'm counting these? So this way had 3, 2, 2, 1, 2, 1, 1, and 0. Alright. This is kind of just a long drawn out way of trying to figure out my probability distribution, because I had to first figure out all the different options for how this could happen. So now we need the probability for each of them. So the probability of having 0 flights on time, that only happened once out of how many trials? So it's 1 out of 16. Let's go ahead and change that to, well, yeah, let's go ahead and do the decimal. So 1 over 16, 0.0625. All right, the probability of having 1 flight on time. So that happened 1, 2, 3, 4 times. So 4 out of, did I get all of them? So what's the probability of that one? 4 out of 16, so 0.25. Then for 2, we could have 1, 2, 3, 4, 5, 6. 6 out of 16. 0.375. For 3, we have 4 of them. And for 4, that happened 1 time. Do you guys see how I got all of those? So this is a method we could use to find our probabilities, but it's fairly time consuming, isn't it? So probably not the ideal method to go about this. Instead, we can look at the binomial distribution, and it gives us a better way for counting these things up. So if we want to get X successes out of a set number of trials, there is a formula for that. In this X, the number of trials, it has to be a whole number. We can't have a portion of 1. So in CX, that is actually a button on your calculator. If you look, if you go to Math, and then go over to Stats, or math probability, it's the third option, NCR. So we can use that to actually calculate these. And then just like everything else, it's on your formula sheet. N is the number of trials, X is the number of successes, P is the probability of success.
NCR.
So we're going to use that formula to try to find them. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, we are finding all of these things. So we need to, before we actually do it, identify what our N and P are in these cases. What is my N? 20 households. Okay, the situation we're looking at is having 3 or more cars. So what's the probability they have 3 or more cars? 0.35. Does anybody have their formula sheet maybe? I was just checking. It doesn't use Q in the formula. It does 1 minus P. They're the same thing. I just wanted to make sure I was writing it down the way the formula had it. So the probability that exactly 5, that's saying my X is 5. So when we go to plug this in, the formula says, if you're looking at your formula sheet, N, C, X. So we have 20, we're choosing 5 of them. P, which is 0.35, to the X, times 1 minus P, so 1 minus 0.35. And I know my X is 5, so I should put that there. To the N minus X power. So 20 minus 5 is 15. So that's like saying we have 5 successes. That means there are 15 failures in this. Okay, and the 20 choose 5 is accounting for all the ways it could happen. If the first 5 are a success and the next 15 are a failure, or the first 15 were failure and the last 5 were success, it accounts for every numerical probability there. So to put it in, you put in the 20, then you go into your math probability, NCR. We want 20 choose 5. 0.35 to the 5th because we have 5 successes. 0.65 to the 15th. Which one?
The 20. No minus.
Put it in parentheses and do 20 and then you push the NCR. It just doesn't put them as subscripts, right? So you go 20 and then go to probability. Yeah, so open a parenthesis, don't close it. Do 20, go into your NCR, then push 5, and then close that parenthesis. So when you type it in, it'll look like this. On those calculators, probably. So just put them in parentheses and you're good. All right. So we get 0.1272. What is the probability that less than 4 have 3 or more cars? So X is less than 4. What does that mean X could be? Okay, so we have to count for 0, 1, 2, and 3. So there's 2 options for doing this. Okay, we can do it on the calculator like we did the last one. I also want you guys to look on your formula packets. There is a table, and in the back. And it kind of looks like this, so you're going to flip towards the back of your packet. And it says at the top, binomial probability distribution. So this has a lot of probabilities already accounted for. Not all of them, so you'll notice it gives us in values, but it doesn't go up forever. It has 1 through 12, and then 15 and 20, and then after that you're on your own. You have to do them on the calculator. It also can't have every possible probability. So you can look across the top, the probabilities we have, 0.1, 0.5, 0.05, so forth. So this probability is our P. Our P on this problem was 0.35. Is that one on our table? Yes. So go to your 0.35 column. And what's my N? 20. So you're going to have to go to the very last page of this packet, or this chart. So did everybody find the page where N has N equals 15, then about halfway down N equals 20? We go over to the 0.35. And then it has the X's. Okay, so I'm going to put this up here just to make sure everybody is reading it correctly. So my probabilities we're looking at, the 0.35 column. Okay, my N is 20. And we needed when X was 0, 1, 2, and 3, correct? So I can look. We are looking for those 4 numbers right there. Did everybody find those on their table? So then we can just copy those down. We don't have to work it out by hand. So my 0 was 0.0002, and we're adding all these together. So my 1 was and do we get 0.0445? Now, I do want to caution you, this table, everything is rounded to 4 decimal places. If you had worked this out on the calculator and just put everything in at once, you would have got 0.0444, just because of rounding error. There's a difference. So I have to know what you're doing. So if you're reading numbers from the table and adding them together, please write down the numbers you're adding together so I know if your answer is 1 digit off, I know, oh, it's because you read from the table, or oh, it's because you did it on the calculator. Okay, because there is sometimes a discrepancy there because of the rounding. All right, so C, what's the probability that at least 4 have 3 or more cars? So at least 4, that means X could be 4 or 5 or 6, all the way up to 20. So we could calculate all of those by hand. We could add them all up from the table. Or what's our third option? Yeah, isn't that just the complement of this one? So we could just do 1 minus the probability we just got. We get 0.9555. Okay, so what's the probability that between 3 and 5 have 3 or more cars? So what are my options for X? X can be 3, or X can be 4, or X could be 5. So easiest option, we can find all three of those numbers by hand, or we can use the table. My n is still 20, my probability is still the 0.35. We are looking at the 3, 4, and 5 rows. So you can get your numbers a couple different places there. And if we do that, we're going to show our work. So write down what we're adding together. So 3 is 0.0323 plus 0.0738 plus 0.1272. And what's that give you? 0.233 what?
33.
Again, if you had calculated that one by hand, it actually came out to be 0.2336 just because of the way the rounding worked out. So I just need to know how you're getting your answers. You have a couple options. Any questions there? Okay, I want to do 2 more slides and then I'm going to stop for today. Mean and standard deviation from this, it's a little bit nicer than just your regular probability distribution formulas. So your mean is just n times p, the number times the probability of success. Standard deviation is the square root of n times p times 1 minus p. So no ugly formulas needed, no big table. We're just plugging into bear, and these are on your formula sheet as well.
So standard deviation is pretty much just NPQ.
The square root of NPQ. Yep. So let's try that. So in this scenario, we know 35% have 3 or more cars. What variable is that? In a sample of 400 car-owning households, what's that? Find the mean and standard deviation. So the mean is n times p. So 400 times 0.35, and that gives us, thank you, standard deviation, square root of n times p times 1 minus p, so square root of 400 times 0.35 times 0.65. And get 9.5394. I am going to stop here for today. We're not done, but we'll finish it on Monday. So you could do, honestly, you could probably do all of it by now if you wanted. Easily at least up through probably 20 or 30. You could do those. We'll just practice some more finding it by hand and using the table on Monday, so get a little more with those. In problem 35, it says to interpret every probability. You don't have to interpret them all, just make sure you know what they mean.